Tonight, we're going to talk about time, not in a hurried way, not as a strict lesson, but as a slow and quiet journey through one of the deepest ideas in physics. Time is so familiar that it can seem impossible to define. We wake up in the morning. We watch the light change through the day. We remember yesterday. We wait for tomorrow. We hear the ticking of clocks. We feel moments pass. We grow older. Stars are born and fade. Clouds form and dissolve. Rain falls and returns to the sea. Waves rise and disappear. Light travels across space. Everything seems to happen inside time. And yet, when we ask what time actually is, the answer becomes strangely difficult. Is time something that flows? Is it something measured by clocks? Is it a dimension like space? Why does time seem to move only forward? Why can we remember the past, but not the future? Why does time slow down near strong gravity or at very high speeds? And what does it mean to say that the universe has an age? Tonight, we will move gently through these questions. You do not need to memorize formulas. You do not need to solve problems. You do not need to understand everything at once. Just listen slowly. Let the ideas pass like minutes drifting across a quiet clock face. If a thought feels clear, let it be clear. If another feels mysterious, let it remain softly mysterious. Time is like that, partly familiar, partly hidden, always present, and still, somehow, difficult to hold. So take a slow breath, let your body settle, and imagine a quiet room at night. A small clock sits on a table. Its hands move almost silently. Outside, the sky is dark. Somewhere far away, the moon is moving along its orbit. The earth is turning. The stars are shining with old light. Your breath rises and falls. The clock continues. Tick, tick, tick. Each tick marks a moment. But the mystery is not only in the clock. It is in the meaning of a moment itself. Tonight, we will follow that mystery slowly. Into clocks, motion, memory, relativity, entropy, the universe, and the quiet feeling of now. Chapter 1, the feeling of time. Before we talk about physics, let us begin with experience. Time is something we feel. A minute can feel short. A minute can feel long. An hour can disappear quickly when we are absorbed in something. Another hour can stretch when we are waiting. A childhood summer can feel enormous in memory. A busy week can pass almost without being noticed. This tells us something important. The feeling of time is not the same as measured time. A clock may measure 60 seconds, but the mind does not always experience those 60 seconds in the same way. Emotion changes time. Attention changes time. Fatigue changes time. Novelty changes time. Routine changes time. When something is new, the mind records more details. Later, the memory may feel longer. When something is familiar and repetitive, fewer details may be stored. Later, the memory may feel shorter. In daily life, we live with both kinds of time, clock time and lived time. Clock time is regular, shared, and measurable. Lived time is personal, flexible, and tied to consciousness. Physics mostly deals with measurable time, the time shown by clocks, the time between events, the time light takes to travel, the time it takes a planet to orbit the sun, the time it takes a wave crest to pass. But the human feeling of time is where the mystery becomes intimate. We do not simply observe time from outside. We live inside it. We are made of processes that unfold in time. Heartbeats, breathing, thoughts, chemical reactions, neural signals, sleep cycles, memory formation. A person is not a static object. A person is a pattern moving through time. This is a gentle way to begin. Time is not only what clocks measure. It is also the background of change. To notice time, we notice change. A shadow moves. A candle burns. A song plays. A drop of rain falls. A child grows. A star ages. If nothing changed at all, it would be hard to say what time meant. So our first quiet idea is this. Time is deeply connected to change. We know time has passed because something is different. Chapter 2, Time and Change. Imagine a perfectly still universe. No motion, no light moving, no particles shifting, no clocks ticking, No thoughts forming, no stars burning, no atoms vibrating, nothing changing at all. Would time still pass? This is a deep philosophical question. Physics usually does not require us to answer it in a final way, but it shows us why time and change are so closely linked. A clock measures time by changing. A pendulum swings. A crystal vibrates. A shadow moves. A sand grain falls. An atomic transition oscillates. Every clock is a physical system that changes in a regular way. We count the changes and call them time. In older clocks, a pendulum swung back and forth. In mechanical watches, gears turn and springs unwound. In quartz clocks, a crystal vibrates at a stable frequency when electricity is applied. In atomic clocks, the frequency of radiation associated with transitions in atoms is used to define very precise time. So time measurement depends on repeating physical processes. A day is measured by Earth rotation. A year is measured by Earth's orbit around the sun. A month was historically linked to the moon cycle. A second is now defined using atomic transitions. We measure time by finding something that changes predictably. Then we count. This makes clocks seem simple, but they are profound. A clock is a small piece of the universe arranged to change regularly. When it changes, it lets us compare other changes. How long did the light take to arrive? How long did the sound last? How long did the planet orbit? How long did the heart beat? Time becomes a way of ordering events. This happened before that. This lasted longer than that. This repeats once every second. This returns once every year. Without time, change would have no sequence. Without change, time would have no visible trace. This does not mean time is only change, but it means change is how time reveals itself. A clock does not create time. It displays change in a controlled way. And by watching it, we coordinate our lives with the larger rhythms of the world. Chapter 3, Natural Clocks. Long before mechanical clocks, nature offered rhythms. The rising and setting of the sun, the changing shape of the moon, the seasons, the movement of stars across the night sky, the return of tides, the migration of animals, the blooming of plants, the cooling of evening air. Humans learn time first from the sky and the earth. A day comes from Earth rotating once relative to the sun. Morning becomes noon. Noon becomes evening. Evening becomes night. Night becomes dawn. This cycle is so deeply familiar that it shapes our bodies. The circadian rhythm is an internal biological cycle of about one day. Light and darkness help regulate it. The body uses the daily cycle of light as a time signal. This is why sunrise can feel awakening, and darkness can invite rest. The month has long been connected to the moon. The moon waxes and wanes. Crescent, half, gibbous, full, then back again. The word month itself is historically related to the moon. The year is connected to Earth's orbit around the sun. As Earth moves around the sun, the tilt of its axis creates seasons. Winter, spring, summer, autumn. The year is not just a number. It is the rhythm of sunlight across the planet. Longer days, shorter nights, changing temperature, migrating birds, falling leaves, growing plants. Natural clocks are everywhere. A tree records years in rings. Ice cores preserve layers of snowfall. Sedimentary rocks hold records of ancient environments. Coral can show growth bands. The universe itself keeps time through change. Radioactive atoms decay at predictable rates. Pulsars rotate and send beams of radiation with extraordinary regularity. White dwarf stars cool over time. Galaxies evolve. The cosmic microwave background carries the imprint of the early universe. Nature does not need clock faces to keep records. It writes time into matter, into cycles, into layers, into light, into motion. A clock on a table is only one expression of a much older truth. The universe is full of rhythms that can be counted. Chapter 4, Mechanical Time. Mechanical clocks change the way humans live with time. A sundial depends on the sun. A water clock depends on flowing water. An hourglass depends on falling sand. A pendulum clock depends on the regular swing of a pendulum. Each one turns a physical process into a measure. The pendulum is especially beautiful. A weight swings back and forth. Gravity pulls it downward. Tension the string or rod guides its motion. For small swings, the period of the pendulum is very regular. This regularity allows clocks to become more accurate. Tick, tock, tick, tock. A pendulum clock is gravity turned into rhythm. A falling weight or coiled spring provides energy. Gears count oscillations. Hands move around the clock face. The invisible passage of time becomes visible as motion. Mechanical clocks help coordinate society, work schedules, navigation, transportation, astronomy, science. Precise timekeeping was especially important for determining longitude at sea. To know where you are east or west, you need to compare local time with the time at a reference location. Accurate marine chronometers helped solve this problem. Time became a tool for locating oneself in space. This is a profound connection. To know where you are, you may need to know what time it is. Time and space are quietly linked even before relativity. Mechanical clocks also change human psychology. Instead of living only by natural cycles, people began to live by measured hours and minutes, appointments, deadlines, schedules, trains, factories, schools. Modern life became organized by clocks. But tonight, we can look at the clock gently, not as pressure, not as urgency, but as a physical instrument, a system of motion designed to count change, a pendulum, a gear, a crystal, an atom, a regular rhythm in a changing world. Chapter 5, Atomic Time. Today, the most precise clocks are atomic clocks. They do not rely on swinging pendulums or turning gears. They rely on the behavior of atoms. Atoms can absorb or emit radiation at very specific frequencies when they move between energy states. These frequencies are extremely stable. A modern second is defined using a particular transition in cesium atoms. This means our definition of time is tied to a repeating process in matter at the atomic scale. The second is not simply a fraction of a day anymore. It is based on a natural frequency of atoms. Atomic clocks are astonishingly precise. They can keep time with errors of only tiny fractions of a second over extremely long periods. This precision matters. Global navigation systems depend on accurate time. Telecommunications depend on timing. Scientific experiments depend on precise measurement. Testing relativity depends on clocks accurate enough to detect tiny differences in time. Atomic clocks reveal something subtle. Time is measured by comparing physical processes. At the deepest level, even a second is not a thing you can hold. It is a count of cycles, a repeated oscillation, a rhythm in matter. There is something calming about this. The modern second is not arbitrary in the casual sense. It is rooted in the quiet regularity of atoms, tiny systems oscillating with extraordinary consistency. Inside laboratories, scientists use lasers, microwaves, magnetic fields, and carefully control conditions to measure time with incredible precision. But the principle is still simple. Find a repeating process. Count it. Use it as a clock. From the sun crossing the sky to a cesium atom changing energy states, timekeeping has always been about reliable change. The scale has changed. The precision has changed. But the pattern remains. A rhythm, a count, a measure change. Chapter 6, Time in Classical Physics. In classical physics, especially in Newton's picture of the universe, time is often treated as universal. There is one time, the same for everyone, the same everywhere. It flows uniformly, independent of the events happening inside it. In this picture, time is like a cosmic clock ticking in the background. Objects move through space as time passes. Forces change motion. Planets orbit. Projectiles fall. Pendulums swing. But time itself remains steady and absolute. This view works very well for everyday life. If you drop a ball, measure a train, swing a pendulum, or time a falling object, Newtonian time is usually good enough. It gives us a simple structure. Position changes with time. Velocity is change in position over time. Acceleration is change in velocity over time. Physics becomes a study of how things change as time passes. This idea is powerful. It allowed Newton to describe motion on Earth and in the heavens with the same laws. A falling apple and an orbiting moon could be part of one system. Time was a parameter through which motion unfolded. In classical mechanics, if you know the positions and velocities of particles at one time, and you know the forces, you can predict future motion, at least in principle. This creates a picture of the universe as a kind of clockwork, a vast machine evolving according to laws, past, present, and future connected by equations. But as science moved into very high speeds, strong gravity, and the microscopic world, this picture became incomplete. Time turned out not to be as absolute as Newton imagined. Still, classical time remains deeply useful. It is the time of ordinary clocks, the time of thrown balls, the time of falling rain, the time of ocean waves, the time of daily life. It is a good first approximation, a calm and practical picture, but not the final one. Chapter 7, The Speed of Light and a New Kind of Time. The story changes when we think about light. Light travels at a finite speed, very fast, but not infinite. In empty space, it travels at about 300,000 kilometers per second. This speed is often written as c. In everyday life, light seems instant. You turn on a lamp, and the room appears lit immediately. But across astronomical distances, light's travel time matters. Light from the moon takes a little over 1 second to reach us. Light from the sun takes about 8 minutes. Light from the nearest stars takes years. Light from distant galaxies can take millions or billions of years. The finite speed of light means that looking far away is looking into the past. But light did something even deeper to our understanding of time. Experiments show that the speed of light in a vacuum is the same for all observers, regardless of their motion. This is very strange from an everyday point of view. If you throw a ball from a moving train, someone outside the train measures the ball's speed differently from someone inside the train. Speeds normally add and subtract depending on motion, but light does not follow this ordinary rule. All observers measure the same speed of light in vacuum. Einstein took this seriously. The result was special relativity. To keep the speed of light constant for all observers, space and time themselves must adjust. Moving clocks tick differently. Moving lengths contract in the direction of motion. Events that are simultaneous for one observer may not be simultaneous for another. This is not because clocks are broken. It is because time is part of the structure of space-time. The speed of light is not merely the speed of a thing. It is a deep rule about how the universe connects events. This was one of the great shifts in physics. Time was no longer absolute. It depended on motion. Chapter 8, Special Relativity and Time Dilation. Special relativity tells us that moving clocks run slow compared with clocks at rest relative to an observer. This effect is called time dilation. It is not noticeable at everyday speeds. A walking person, a car, a train, or even an airplane moves far too slowly compared with the speed of light for the effect to be obvious without precise instruments. But at speeds close to the speed of light, time dilation becomes dramatic. Imagine a spaceship traveling very fast past Earth. From the point of view of people on Earth, the clock on the spaceship ticks more slowly. From the point of view of the astronauts, their own clock feels normal. Their heartbeat feels normal. Their thoughts feel normal. Their instruments behave normally. Time has not slowed in their personal experience. Rather, when comparing different frames of motion, the measurements of time differ. This is subtle. There is no universal clock that everyone agrees on in all circumstances. Each observer carries their own proper time. Proper time is the time measured by a clock moving along with that observer. This leads to the famous twin scenario. One twin stays on Earth. The other travels at high speed through space and returns. The traveling twin may have aged less than the twin who stayed behind. This is not science fiction in principle. Time dilation has been measured. Particles moving at high speeds live longer from our perspective than they would have at rest. Precise clocks flown in aircraft or placed on satellites show relativistic effects. Special relativity teaches that time is personal in a physical sense, not merely psychologically personal, but physically dependent on motion through space-time. This can feel unsettling, but it can also feel beautiful. Time is not a rigid river flowing identically for all beings. It is woven with motion. The path you take through spacetime affects the time you experience. Chapter 9, Simultaneity. Special relativity also changes the idea of simultaneity. Simultaneity means two events happening at the same time. In everyday life, this seems straightforward. Two lamps flash at once. Two bells ring at once. Two doors close at once. But when observers move relative to each other, they may not agree about whether distant events happened at the same time. This is called the relativity of simultaneity. Let us imagine it gently. Suppose two flashes of light happen at opposite ends of a moving train. An observer standing at the middle of the train might receive the light from both flashes at the same moment and conclude the flashes were simultaneous. But an observer standing on the platform, watching the train move, may receive the light in a different way and conclude that one flash occurred before the other. This is not because either observer is confused. It is because time and space are linked and the speed of light is fixed. Different states of motion slice spacetime into now differently. This means there is no single universal present that all observers must share across the entire universe. The word now is local and relational. For nearby everyday life, this does not cause problems. We can coordinate clocks well enough. We can agree on schedules and events. But on cosmic scales and at high speeds, simultaneity becomes subtle. This is one of the most profound ideas in physics. The present moment, which feels so absolute to us, is not absolute in the same way everywhere for everyone. There is still cause and effect. There is still structure. But the universe does not provide a single global clock face visible to all observers. Time is woven into space-time. Motion changes how we divide events into past, present, and future. This can feel abstract, so we can let it rest gently. The main idea is enough. At deep levels, time is not the same for every observer. Even the idea of at the same time depends on motion. Chapter 10, Spacetime. Einstein's theories led to the idea of spacetime. Before relativity, space and time were often treated separately. Space was where things happened. Time was when they happened. But relativity shows that space and time are linked. They form a single four-dimensional structure called spacetime. An event is something that happens at a particular place and time. For example, a light flashes in a room. That flash has a location in space and a moment in time. Together, these define an event in space-time. Objects trace paths through space-time. A person sitting still in a chair may not move much through space, but they move through time. A planet moves through space as time passes. A photon moves through space at the speed of light, following a light-like path. In space-time, motion through space and motion through time are related. The faster something moves through space relative to an observer, the more its time differs from that observer's time. This is a gentle way to think about special relativity. Your path through space-time affects the time you measure. Space-time diagrams can represent time on one axis and space on another. Light paths form diagonal lines. The speed of light creates a boundary called the light cone. Events inside your future light cone can be influenced by you. Events inside your past light cone can influence you. Events outside the light cone are too far away in space and too close in time for light or any signal to connect them. The light cone shows the structure of causality. What can affect what? What can be known? What remains unreachable for now? Space-time is not just a mathematical convenience. It is how modern physics understands a stage of events. And in general relativity, space-time is not fixed and flat. It can curve. Mass and energy shape it. Gravity is connected to that curvature. This brings us to another way time changes, through gravity. Chapter 11, Gravity and Time. Gravity affects time. This is one of the most extraordinary ideas in physics. A clock closer to a massive object ticks more slowly than a clock farther away. This effect is called gravitational time dilation. Near Earth, the effect is tiny, but it is real. A clock at sea level ticks slightly more slowly than a clock on a mountain. The difference is extremely small, but precise clocks can measure it. Near a very massive object, like a neutron star or a black hole, gravitational time dilation can become much stronger. In general relativity, gravity is not simply a force pulling objects. It is related to the curvature of spacetime. Mass and energy curve spacetime. Objects follow paths through that curved spacetime. Time itself is part of what curves. This means gravity does not only shape motion through space, it shapes the rate of time. Imagine two clocks, one deep in a gravitational field, one far away. The deeper clock ticks more slowly compared with the distant one. If the clocks are later brought back together, they may disagree slightly. This is not because one was faulty. They traveled through different gravitational conditions. They experienced different amounts of time. This effect matters for GPS satellites. The clocks on GPS satellites are higher above Earth and moving relative to us. Both special relativity and general relativity affect them. If these effects were not corrected, GPS positioning would quickly become inaccurate. So when a phone gives directions, it quietly depends on the physics of time. Relativity is not only about distant stars. It is built into modern navigation. Time is practical. Time is cosmic. Time is local. Time is gravitational. A second is not simply the same everywhere in the universe. It depends on where you are and how you move. Chapter 12, Black Holes and the Edge of Time. Near a black hole, gravity becomes extreme. A black hole is a region where space-time is curved so strongly that nothing can escape from inside the event horizon, not even light. The event horizon is the boundary of no return. Outside it, escape may still be possible. Inside it, all future paths lead inward. Time near a black hole behaves in strange ways. For a distant observer, a clock falling toward the event horizon appears to slow down. The light from the clock becomes increasingly redshifted and faint. It seems to approach the horizon more and more slowly. But for the falling observer, time feels normal locally. They cross the horizon without experiencing their own clock stopping. This difference comes from the relativity of time and the extreme curvature of space-time. Black holes force us to think carefully about what time means for different observers. Inside the event horizon, the structure of space-time changes so radically that moving toward the center becomes as unavoidable as moving toward the future. This is difficult to visualize, and it is okay if it remains mysterious. Black holes are places where our intuition becomes weak, but they teach us something important. Time is not separate from the gravitational structure of the universe. Near extreme gravity, time itself behaves differently. Black holes also connect time to information, quantum physics, and thermodynamics. Stephen Hawking showed that black holes are not entirely black in quantum theory. They can emit radiation, now called Hawking radiation. This leads to deep questions about entropy, information, and the fate of matter that falls into black holes. We do not need to explore all of that tonight, but we can notice the direction. When physics studies black holes, time becomes one of the deepest mysteries. What happens to information? How does quantum theory combine with gravity? What is the final fate of a black hole? At the edge of a black hole, time is no longer ordinary. It becomes part of the mystery itself. Chapter 13, The Arrow of Time. In daily life, time seems to have a direction. We remember the past. We do not remember the future. Eggs break, but do not unbreak. Ice melts, but melted water does not spontaneously refreeze into the exact same cube without help. Smoke spreads through a room, but does not gather back into a small stream. A cup can fall and shatter, but shattered pieces do not leap back together into a cup. This direction is called the arrow of time. At the microscopic level, many laws of physics work almost the same forward and backward in time. If you watch a video of two ideal particles colliding, the reverse might also look physically possible. But in the macroscopic world, time has a strong direction. Why? The answer is connected to entropy. Entropy is often described as disorder, but that word is only a rough beginning. A better way is to think of entropy as related to the number of microscopic arrangements that correspond to the same large-scale state. There are many more ways for a room to be messy than tidy. Many more ways for smoke to be spread out than gathered in one corner. Many more ways for heat to be evenly distributed than concentrated in one small place. Systems tend to move from less probable arrangements to more probable arrangements, from low entropy to higher entropy. This tendency gives time a direction. The second law of thermodynamics says that in an isolated system, entropy tends to increase. This is one of the most important laws in physics. It explains why heat flows from hot to cold, why processes are irreversible, why energy becomes less available for useful work, and why the future feels different from the past. The arrow of time may be rooted in the fact that the universe began in a very low entropy state. From that special beginning, entropy has been increasing. Stars burn, heat spreads, structures form and evolve. Life uses energy flows to maintain local order while increasing entropy overall. The arrow of time is not merely psychological. It is written into thermodynamics. Chapter 14, Entropy and Everyday Life. Entropy can feel abstract, so let us bring it into ordinary life. Imagine a cup of hot tea in a cool room. At first, the tea is warmer than the air. Heat flows from the tea into the surroundings. The tea cools. The room warms by an extremely tiny amount. Eventually, the tea and room approach the same temperature. You never see a cup of lukewarm tea spontaneously gather heat from the room and become hot again while the air cools. That would not violate energy conservation if arranged carefully, but would be extraordinarily improbable as a spontaneous process. Entropy points one way. Heat spreads. Differences smooth out. Now imagine perfume released in one corner of a room. At first, the scent is concentrated. Over time, molecules spread through the air. They move randomly, collide, and diffuse. Eventually, the scent becomes more evenly distributed. You do not see the molecules spontaneously gather back into the bottle. Again, entropy increases. Or imagine a deck of cards arranged perfectly by suit and number. Shuffle it. It becomes disordered. There is only a small number of highly ordered arrangements, but an enormous number of mixed arrangements. Random shuffling almost always moves from order toward disorder. These examples are not merely about mess. They are about probability. High entropy states correspond to many microscopic possibilities. Low entropy states correspond to fewer. The universe naturally evolves toward states that are more statistically likely. This statistical direction gives our everyday world its irreversible quality. This is why time feels like it flows from a structured past toward a more dispersed future. A candle burns. The wax does not unburn. A sound fades. The air vibrations do not spontaneously reassemble into the original note. A wave breaks into foam. The foam does not gather into the exact same wave and retreat backward. Entropy is a soft but relentless spreading of possibility. The world becomes harder to reverse because the details become dispersed. Chapter 15, Memory and the Past. We remember the past, not the future. This seems obvious, but it is connected to the arrow of time. A memory is a physical record. It exists in the brain as patterns of connections, chemical states, and neural structures. A photograph is a physical record. Light affected a sensor or film. A fossil is a physical record. A footprint is a physical record. Tree rings are physical records. Records form because the past leaves traces in the present. A wave leaves ripples. A foot leaves a print. Light leaves an image. A collision leaves marks. Events become recorded through physical interactions. These records are possible because entropy increases. To make a record, energy is used and entropy is produced. The past can be known because it has left traces. The future has not yet left traces in the same way. This is why memory points backward. The brain is not receiving signals from future events. It is storing traces of past events. Psychological time follows physical time. We experience now as the edge between memory and expectation. Behind us are records. Ahead are possibilities. This is one reason the present feels special. It is where records of the past meet predictions about the future. But in physics, especially relativity, the idea of a universal present becomes complicated. Still, for living beings, the present has practical meaning. It is where decisions happen, where senses receive information, where memories update, where the body moves. Time is not only measured by clocks. It is also organized by memory. A person is a being with records. We carry the past in our nervous systems, bodies, habits, and stories. Our sense of time is built from change, memory, and anticipation. This makes time emotional. not only physical. A clock tells us that seconds passed. Memory tells us that a life passed through them. Chapter 16, Time in Quantum Physics. Quantum physics treats time in a special way. In ordinary quantum mechanics, time is often a parameter. The wave function of a system changes with time according to the Schrödinger equation. But time itself is not usually treated like a quantum observable in the same way position or momentum can be. This creates deep questions. In quantum physics, particles can exist in superpositions of states. Measurements have probabilistic outcomes. The act of measurement seems to play a special role. But time continues as the background parameter in which the quantum state evolves. When physicists try to combine quantum mechanics with general relativity, time becomes even more mysterious. General relativity treats spacetime as dynamic. It can curve and change. Quantum theory treats matter and fields probabilistically. A full theory of quantum gravity would need to reconcile these views. This is one of the major open problems in physics. What is time at the deepest level? Is it fundamental, or does it emerge from something deeper? Some approaches suggest that time may not be basic in the way we experience it. It may emerge from relationships between physical systems, or from thermodynamics, or from entanglement, or from the way information is structured. These ideas are still active areas of research. We do not need to solve them tonight. But it is peaceful to know that even physicists do not treat time as fully understood. Time is not a finished chapter. It is an open question. Quantum physics reminds us that the deepest nature time may be stranger than clocks suggest. At human scale, time flows. At relativistic scale, it bends and depends on motion. At thermodynamic scale, it has an arrow. At quantum gravity scale, it may be something we have not yet fully imagined. The mystery remains, and that is part of its beauty. Chapter 17, Time and the Universe. The universe has a history. Modern cosmology tells us that the observable universe has been expanding for about 13.8 billion years. This number is not guessed casually. It is inferred from many kinds of evidence. The expansion of galaxies, the cosmic microwave background, the abundance of light elements, the large-scale structure of the universe. When we say the universe has an age, we mean that the hot, dense early state we call the Big Bang occurred about 13.8 billion years ago in our current cosmological model. The Big Bang was not an explosion into empty space. It was an expansion of space itself from a hot, dense early condition. Time, in this picture, is part of the universe's structure. Asking what happened before the Big Bang is difficult, because our usual understanding of time may not apply in the same way near the earliest moments. Some theories suggest there may have been earlier phases. Others suggest time itself may have begun with the Big Bang. We do not know with certainty, but we do know that the universe has evolved. It cooled, particles formed, atoms formed, light began traveling freely, stars formed, galaxies formed, planets formed. Life emerged on at least one world. Conscious beings began asking about time. The universe is not static. It has a story, a timeline, a sequence of transformations. Cosmic time gives us a way to speak about that sequence. But because light takes time to travel, our view of the universe is layered. Nearby galaxies are seen more recently. Distant galaxies are seen as they were long ago. The cosmic microwave background is a baby picture of the universe, light from a much earlier time. Looking outward is looking backward. Telescopes are time machines in a physical sense. They collect old light. They let us see stages of cosmic history. Time is written across the sky. Chapter 18, The Future of Time. If the universe is a past, it may also have a future. What happens to time in the far future? This is a large question, and the answer depends on cosmology. Current observations suggest that the expansion of the universe is accelerating, driven by something we call dark energy. We do not yet fully understand dark energy, but if acceleration continues, distant galaxies will move beyond our observable reach. Over immense timescales, stars will use up their fuel. New star formation may slow and eventually fade. Stellar remnants will remain. White dwarfs, neutron stars. Black holes. Planets may drift in darkness. Black holes themselves may slowly evaporate through Hawking radiation over unimaginable timescales. The universe may move toward a state of increasing entropy, with energy spread thinly and few available differences left to drive change. This possible future is sometimes called heat death. The name sounds dramatic, but we can think of it quietly. A universe where usable energy gradients fade, where stars are gone, where processes become slower and rarer, where time continues perhaps, but meaningful change becomes sparse. This is not something to fear in daily life. The timescales are far beyond human imagination, far beyond the lifetime of Earth, far beyond the lifetime of the Sun. But it shows how time and entropy are connected on the grandest scale. The future of the universe may be the long unfolding of the arrow of time, from hot, dense beginnings, to stars and galaxies, to life and thought, to expansion and cooling, to a distant, quiet fading. Physics lets us imagine these enormous timescales, not to make us feel small in a frightening way, but to place our moments inside a vast story, a human night, a breath, a second, a lifetime, a star, a galaxy. All are different scales of time. Chapter 19, Time and Life. Life is deeply temporal. Living things are processes. They grow, repair, move, sense, respond, reproduce, age. Every cell contains clocks of a kind, chemical cycles, gene expression rhythms, metabolic pathways, signals that rise and fall. The body has many rhythms: heartbeat, breathing, sleep cycles, hormone cycles, circadian rhythms. The brain itself is full of oscillations. Electrical activity rises and falls in patterns. During sleep, certain brain waves become slower and more synchronized. The body does not simply exist in time. It is organized by time. Light helps set the circadian rhythm. Morning light signals wakefulness. Darkness signals rest. Meals, temperature, movement, and social activity also shape biological timing. Plants have rhythms too. Flowers open and close. Leaves move. Photosynthesis follows daylight. Animals migrate, hibernate, hunt, sleep, and wake according to time patterns. Life is timing. The right event at the right moment. A seed sprouting when conditions are good. A bird migrating with the season. A cell dividing after preparing. A heart beating rhythmically. A brain entering sleep. Time is not only cosmic and mathematical. It is bodily. It is living. When you begin to feel sleepy, your body is not failing at wakefulness. It is following rhythms. Signals accumulate. Hormones shift. Neural activity changes. Temperature may drop slightly. Attention softens. The body turns toward rest. This is time inside life. Not a clock face, but a biological tide. Chapter 20, The Present Moment. The present moment feels special. It is where experience happens. The past is remembered. The future is imagined, but the present is felt. And yet, the present is hard to define precisely. In neuroscience, the brain integrates information over short intervals. What we experience is now maybe a small window, not an infinitely thin slice. Sound, sight, sensation, and thoughts are combined into a coherent present. Light takes time to reach the eyes. Sound takes time to reach the ears. Nerve signals take time to travel. The brain takes time to process. So even the present we experience is constructed from signals that arrive with tiny delays. The now is not as simple as it feels. In relativity, the present is also not universal across vast distances. Different observers may disagree about which distant events are simultaneous. So the physical present is local and subtle. But psychologically, the present is where awareness rests. A breath, a sound, a sensation, a thought. The present is where the mind meets the world. For a sleep video, this can be comforting. You do not need to hold the whole past. You do not need to solve the whole future. You can rest in a small present window. The sound of the voice, the weight of the body, the room around you, the next breath. Physics can make time seem vast and strange, but experience brings it back to something simple. This moment, then this one, then this one, each moment arriving and leaving, like waves on a quiet shore, like drops of rain on a window, like light crossing a room. Chapter 21, Time, Sleep, and the Night. Sleep is one of the most intimate experiences of time. When we sleep, our sense of time changes. Hours may pass without being noticed. A dream may feel long, but take only part of the night. A night of deep sleep may seem to vanish. We close our eyes. Then morning arrives. The body continued its processes. The heart kept beating. Breathing continued. Cells repaired. Memories were processed. Brain activity shifted through stages. But conscious time became different. Sleep reminds us that time is not only measured outwardly by clocks, it is also shaped by awareness. A clock may count 8 hours, but the sleeper may experience almost no passage at all. This is one reason sleep feels like a small mystery. We disappear from ordinary time for a while, then return. The night has passed. The body has changed. The world has turned. The sun is in a new place. The brain carries traces of dreams or none at all. Sleep is also rhythmic. It moves through cycles. Light sleep, deep sleep, REM sleep, dreaming, back again. The cycles are not identical, but they follow patterns. The night is structured, not empty, not simply a gap. It is time used differently. Restorative time, hidden time, biological time. If you are listening to this while falling asleep, then time may already be softening. The words may become less distinct. The ideas may begin to drift. The clock may continue. But your experience of time may loosen. That is okay. The story of time can become background. The night can carry you forward without effort. Chapter 22, a gentle summary. Let us gather the story softly. We began with the feeling of time. How a minute can feel long or short depending on attention, emotion, and memory. Then we saw that time is deeply connected to change. Clocks measure time by changing regularly. Pendulums swing. Crystals vibrate. Atoms oscillate. The earth rotates. The moon orbits. The seasons return. We explored natural clocks. The sun, the moon, the year, tree rings, radioactive decay, pulsars. Nature writes time into cycles and records. We looked at mechanical time, gears, pendulums, chronometers, then atomic time, the modern second defined by the rhythm of atoms. We entered classical physics, where time is treated as universal and steady. Then light led us into relativity. The speed of light is the same for all observers. To make that true, space and time must be linked. Moving clocks tick differently. Simultaneity becomes relative. Space-time replaces separate space and time. Gravity also affects time. Clocks deeper in gravity tick more slowly than clocks farther away. Near black holes, time becomes extreme and strange. We explore the arrow of time, the fact that the past and future feel different. Entropy increases. Heat spreads. Broken things do not spontaneously unbreak. Records form in the present from events in the past. Memory points backward because the past leaves traces. We touch quantum physics, where time remains mysterious. We looked at cosmic time, the age and future of the universe. We saw that life is full of rhythms. Heartbeat, breath, circadian cycles, sleep, and finally, we return to the present moment, the place where experience happens, the small window where awareness rests. Time is measured by clocks, shaped by motion, bent by gravity, directed by entropy, recorded by memory, stretched across the universe, and felt quietly in the body. Chapter 23, Closing Reflection. Time is with us so constantly that it can disappear from attention. We look at clocks. We follow schedules. We remember yesterday. We expect tomorrow. But beneath all of that is something deeper. The quiet unfolding of change. A leaf falling. A wave passing. A beam of light traveling. A drop of rain returning to the sea. A planet turning. A star burning. A life moving from one moment to the next. Physics does not make time less mysterious. In some ways, it makes time more mysterious. Newton gives us steady time. Einstein gives us flexible time. Thermodynamics gives us the arrow of time. Quantum physics gives us questions about time. Cosmology gives us the age of time. Life gives us lived time. Sleep gives us softened time. And here, in this quiet moment, time becomes simple again, a breath, then another, a word, then silence, a thought, then drifting. You do not need to understand time completely tonight. No one does. It is enough to rest inside it, to let the seconds pass without chasing them, to let the mind loosen its grip on before and after. The clocks can continue. The earth can turn. The moon can move. The stars can shine with ancient light. The universe can unfold at its own pace. And you can rest. For now, there's only this gentle moment, and then the next, and then the next, softly, quietly, until the moments blur into sleep. Sleep well. If you enjoyed this calm journey through time, you can return anytime for more gentle physics stories about energy, fire, stars, black holes, quantum physics, and the quiet laws of the universe. For now, thank you for listening, and good night.